Now we're going to talk about an experimental instrument that is very convenient to measure heats of reaction. So sometimes if you look at your any food that you may eat that contains the calorie content, you may want to know why is it that, how can they know what energy that food contains. So for example, if you have a donut and it says, well, the calorie content in here is, and I'm going to make this up, 500 calories. How do they know that? Well, a good way to know is to take the donut and burn it. Burn it, okay, and measure the heat that this gives off, okay? Of course, with some imagination, again, you'll have to forgive my drawing skills. How can we measure the heat, something so kind of abstract? How can we measure heat after burning something? Because of course the heat that this reaction will give off, it will be the calories that this donut contains. How can we measure heat? Well, something that we can really measure, as you saw in the previous video, is that we can measure the change of temperature. And we can associate the temperature into heat, and this would be the change of enthalpy of our reaction. If we know the mass of the donut and the heat capacity of our experimental device, we can relate change of temperature and heat. And this is what the calorimeter does. The calorimeter is a device that allows you to measure increment of temperature. So in this case, the most simple calorimeter is the coffee cup calorimeter. You just have a styrofoam cup that you cover, you put water in it, you put a thermometer, and it tries to keep the heat from going off. So the exchange between your sample, in this case, it cannot be the donut because it would not burn underwater, but it's a sample, and in this case it's water, okay? For donut it would have to be a little bit more complicated. But the idea is that the change in temperature of water is associated to the heat that your system contained, okay? So this is a very common experimental device to measure heats of reaction or heats of any physical or chemical change. So let's run a simple problem. In this case, it says that you have 4 different hot liquids at 50 Celsius, and they are placed in 4 different cups. So we have 4 different cups. 4 different cups. 1, 2, 3, and 4. Okay? And they are all at 50 degrees. Not the cup, but the liquid. 50 Celsius. Okay? And it says that with time, of course, the coffee cup with styrofoam will eventually lose some heat and will reach a thermal equilibrium with the room at which it's at 20 Celsius. Okay, and it's asking, so that will take several hours. But it's asking just after just 1 hour before the thermal equilibrium is reached, which cup will have the lowest temperature? Okay, in other words, which cup will have lost the highest amount of heat? Okay, because of course if it has lost temperature, it's because it has lost heat. All right, so let's look at these different the 4 different liquids. And the important part, because all the masses are all the same, something that we said is that the largest increment of change will be because of the smallest heat capacity. Okay, if you remember from the previous slide, because the system and the mass is the same, the body with the lowest heat capacity will be the one that will have the lowest, I'm sorry, the body that will lose the temperature faster will be the one that has less pockets, the one that will has the lowest heat capacity. So what is the liquid with the lowest heat capacity? In this case, carbon tetrachloride is by far the one with the lowest heat capacity. It will have less pockets of energy, if you will. Therefore, it would lose the energy faster. So in this case, the answer is carbon tetrachloride.